Okay. So what we're going to talk about today is we're going to talk about 15.7 and a bit of 15.8. I just realized I hadn't posted the notes until when I got onto the computer last night and noticed they hadn't been posted yet, and then I didn't print these out because I have no way to keep my backpack from turning into a wet pile of mess. If I bring paper in my backpack right now, it's just going to be gross. So I will print those on request or next week when it dries out a little bit. So what we're talking about basically is coordinate systems that describe what happens when the region that you're working with, a three-dimensional region that you're working with, is not well suited to talking about rectangular coordinates. So in 2D, we had the case that there were two different kind of regions that we considered. There were sort of rectangles, and then what we called elementary regions, or type 1 or type 2 is what the book calls them, but regions that are described by inequalities in x and y in a really nice way. And in this context, we used Cartesian coordinates, dx, dy. So if I want to calculate an integral over a region that is well suited to working on in rectangles, I use rectangular coordinates to do it. If I'm working on a region that's well suited to working on in a circular way of thinking, so that would be a region where I have some kind of function f is, or r is equal to f of theta, where theta goes from a to theta is equal to b, that would be really difficult to work with in a rectangular setup, because where do you even begin with something like that? If I want to write this in dx dy, there's no functions of x or y that describe this region well. But if I used polar coordinates, it was really easy. I would let r go from 0 to f of theta, and theta go from b to a, and that's a really nice way of describing this region that does not work in rectangular coordinates. And then our dA unit in that context was r dr d theta. So when I had notions where thinking about things as pieces of circles was natural, I used polar coordinates. And when I have regions that it's natural to think about them as broken up into rectangles or bounded by x's and y's, I use rectangular coordinates. So the point of 15.7 and 15.8 is to extend that kind of thinking to the ideas that we learned about in 15.6. So in 15.6, we studied integrals where the natural way to break up the region was into little sort of cube things, where my dv unit was dx, dy, dz in some permutation, right? Some order dx, dy, dz. So in 15.6, we did triple integrals where I broke up my little volumes in these little cubes. And the natural regions that we considered were things like, oh, well, if I have a tetrahedron, we did a bunch of these tetrahedron problems, I can easily think about this in rectangular coordinates because everything's built out of straight lines. Lines and planes or surfaces are really easy to work with in rectangular coordinates, Cartesian coordinates. So what we're going to do is we're going to look at two different kinds of regions that are not well described by rectangular coordinates. And the two that we're going to look at are things that look like cylinders, so surfaces that sit along an axis over some kind of circular domain. So these are called cylindrical coordinates. And the idea is, if I'm integrating over a region in 3 space that looks more like a cylinder than something bounded by flat stuff, maybe I shouldn't be using rectangular coordinates. Maybe I should be using something that takes advantage of the fact that there's circles running around. This is the subject of 15.7. And then 15.8, which is about spherical coordinates. That's regions that look like this. So if I have chunks of a sphere, instead of cylinders as being the things I'm integrating over, if I have spheres that I'm integrating over instead, I want a coordinate system that takes advantage of the fact that I have all this symmetry in the system. Right? And these things show up in physical applications in a couple of really natural ways. Probably the first time you see this kind of setup is if you think about current flowing through a wire, the magnetic and electric fields around it extend radially from the wire, right? So the magnetic field sort of circles the wire in a cylindrical way. So if I want to study current flow, cylindrical coordinates is a common way to do it. Or the flow of fluid through a pipe is another thing that you can think of as being able to be studied in cylindrical coordinates. Right. Spherical coordinates show up in things like the emanation of electric field from a particle emanates in 3 space as a sphere. Gravitational fields tend to be easy to express in spherical coordinates. So there's a lot of physical motivation for the study of these things. If you happen to be doing something in aero or electrical or mechanical where you're working with control of robots or autonomous systems or navigation, the standard of choice for navigation systems is actually spherical coordinates. Right? So in an aircraft you would think like pitch and yaw are like angles, right? And that's like there's 2 angles that are chosen here. Okay. So let's start with 15.7, and I'm going to motivate this with a question that's kind of nasty if we do it in rectangular coordinates. So if I asked you to do the following integral, the integral of x squared dv over the region, say, I don't know, R for region, where R is a right circular cylinder from z equals 1 to z equals 3 above the circle x squared plus y squared is less than or equal to 1. So the picture here is the region that I'm integrating over is a cylinder. It's oriented along the z-axis. It's a right circular cylinder. That's the z-axis right there. It's stuck between the planes z is equal to 1 and z is equal to 3. And if we wanted to approach this problem with the ideas of 15.6, I need to be able to describe that cylinder in Cartesian coordinates. So we should do that just as a last bit of practice here. I need some system of inequalities that describes that region so that I can replace this with a triple iterated integral. So pretty easy to figure out what the z value should be. I'm going to find a base that this thing sits over the top of, which is this disk in the xy plane. So in the xy plane, I'm inside the disk x squared plus y squared is less than or equal to 1. For any fixed value of x and y, you can imagine that the disk is down here. For any fixed value of x and y, in the cylinder that I'm studying, my z values start at the bottom plane and then go up until I leave the cylinder at the top plane, right? So the z values are bound between 1 and 3 for any particular value of x and y. And now I need to characterize what's going on in the disk itself. So I'm going to write y as a function of x. So for a fixed value of x, my y values travel from y is equal to the square root of 1 minus x squared on top, and y is equal to minus the square root of 1 minus x squared on bottom. Ew, that's nasty. So for a fixed value of x, my y values travel from the bottom half circle to the top half circle, with the irritation of the plus and minus because circles aren't functions. So my y values go between these guys. And then finally my x values go between 1 and minus 1. And so if I want to set this up as a triple integral, I can use the inequalities to write down the integral from 1 to 3, and that's dz. And then the integral from the square minus the square root of 1 minus x squared to the square root of 1 minus x squared, and that's my dy. And then I integrate from minus 1 to 1, and that's dx. And you should already be shuddering, because when I integrate the y's out, which aren't there, I'm going to be left with terms that look like x squared times the square root of 1 minus x squared, which is inverse trig substitution. Ugh. That sucks. And the reason it sucks is because everything about the setup of this problem suggests that there should be circles involved, and we didn't use them. So, when I have domains that are naturally thought of as cylinders, I need a coordinate system that reflects that. So this is 15, 7. We're going to build this coordinate system, and then we're going to go back and reevaluate this integral with respect. I'm going to rebuild the integral with respect to cylindrical coordinates. Cylindrical coordinates. Okay, so first I'm just going to tell you what they are. So this is the definition, and I should say this is with respect, that's what WRT means, with respect to the cylindrical axis being the z-axis. X is equal to r cosine theta, y is equal to r sine theta, and z is equal to z. So that is the spherical coordinate transformation. This is the defining set of relations that tell you, given r, theta, and z, how to get the x, y, and z back out of it. So let me draw a picture of how we think about cylindrical coordinates. So if I'm in the x, y, z plane, and I have a point, let's see, I'll go out this many units and over this many, and then up z. So this is x, and this is y, and this is z, so that this point right here is located at x, y, z. In cylindrical coordinates, what we're saying is, okay, keep the z value what it is. Just keep z. Then look at the shadow of that point in the xy plane. This angle right here is the angle theta. And the length of that line segment down here is r. So you're basically saying use polar coordinates in two of the variables and then just go up or down in the third one. So if I want to dictate where a point is in cylindrical coordinates, I've got some sort of positive axis. The first thing I do is I rotate by an angle of theta. Then I go out a certain number of units, that's the r value, and then from there I just lift straight up parallel to the axis, and that's the z value. So it's circular in two of the coordinates and Cartesian in the third. Now if I want to come up with a way of looking at a triple integral, not in terms of dx, dy, and dz, but with respect to these coordinates, I need to think about breaking all of R3 up into little bits of volume. And the little bits of volume that you might get if you were using a cylindrical picture like this would be, let's actually draw what one of these would look like. So if I had a little tiny change in angle here, you would get something that looked like this. And a little tiny change in radius would be a base that looks something like that. So a little polar bit down there in the xy plane. And then if I had a little bit of change of z, so imagine up here, we've got from this point that we've chosen, we go out this way a little bit, and then we arc, and we go out this way a little bit, and then we arc. And if I want to put a little change in z in there too, I get kind of this, I don't know how to describe this thing. What does it look like? Yeah, but it's also bent. If I draw this picture like more exaggeratedly, you have kind of something that looks like this, where this is curved and this is curved, and then the figure goes up and follows the same curve, comes out. Let's see if I can erase that stuff. Like a corn kernel almost, would be one way of thinking about it. Okay. So what I need to do is come up with some way of thinking about what the dv of that would be. Right now what I'm thinking is, the way I've measured this is this distance right here is delta r, a little tiny change in radius, because that's what happened down here. This is in the radial direction. And then from when we talked about polar coordinates, the length of that side right there is about equal to r delta theta. The little tiny change in theta tells you that there's a little tiny unit of arc length down here. So this bit over here has length about equal to r delta theta. And then this is a little tiny change in the z direction. So that should be delta z in this direction. So that little tiny piece of R3 that I've built, if I chop up all of R3, I chop it up into these little bits, should tell you that a little tiny bit of volume in this coordinate system, delta V, should be equal to R dr, well, R, delta theta, delta Z. So just like in the polar coordinate system, I can't just take dx, dy, dz and replace it with r, d theta, dr, d theta, dz. I need dv is equal to r, dr, d theta, dz in an order that makes sense. Always r has to go before theta because we have to integrate the r's out first, basically. Now, there's actually a bigger picture as to why this is the change in volume here, which you need linear algebra to know. So if you really want to know this, take linear algebra, or 244, which I'll teach next time. And then you can take 304, which may or may not exist after we change to semesters. And then I'd be able to show you that actually what we did here is we took a determinant of the matrix of first derivatives that we got from this coordinate change, and that works in general and not just in this specific case. If those words mean nothing to you, they will someday. We'll revisit it. So really what I want you to think is, if I took a region in cylindrical coordinates and broke it into little bits, that's what the bits would look like, and I can approximate their volume just by doing geometry. Okay, so what we have now is the last piece that we need to reevaluate this integral. dv is equal to r dr d theta dz. Let's go back and look at this integral again. All right, can I erase this picture? Are you still working on it? I will say that I know some of you are taking advantage of this. I don't mind if you snap pictures of the board. Like, I will have this on video as well. Okay, so the integral that we started with was the triple integral over r of x squared dv, and r was a cylinder that went from z is equal to 1 to z is equal to 3, and the bounding circle at the bottom was x squared plus y squared is less than or equal to 1. So I'm going to suggest that instead of thinking of this in x and y coordinates, we should think about it in r, theta, and z coordinates. And when I look at that region, what I see is, okay, my radius values here, once I've picked the axis, this is the cylindrical axis is going to be z, so I pick the other two variables to think of as being the r and theta plane. That circle in the r and theta plane is the circle of radius 1. And the z values run between 1 and 3. Now, I don't know if it should be surprising or not that cylinders would be particularly easy to describe in cylindrical coordinates. But, like, basically, in cylindrical coordinates, a cylinder is a cube. Right? It's bounded by constants. That's just one of the nice things about cylindrical coordinates. So, why would you use cylindrical coordinates on a cylinder? Because your limits of integration are going to be constants instead of functions. So if I rewrite the same exact integral that we have written right there, but with respect to this, now I could just write, oh, so it's the integral from 1 to 3 of the integral from 0 to 2 pi of the integral from 0 to 1. Oh, darn, there's an x squared right there. But I know that x squareds can be replaced with r cosine thetas, or x's can be replaced with r cosine thetas. So I'm going to get an r squared cosine squared of theta, r d, what's 0 to 1? R d theta dz. And that is a much easier integral than that one. Much easier. No inverse trig substitution, no fancy integration by parts, or if you decide to do it that way, no power series approximations, no functions in the limits of integration. Because we carefully chose a coordinate system that agreed well with the problem we were studying, we get this really easy integral out the other side. A classic exercise on an exam in in this chapter is to give you an integral like this and actually have you compute it. If you do it this way, it's easy. If you do it that way, it's basically impossible. And it's a way of testing, like, did you choose the right coordinate system? I'm not sure I would actually make you do the integral, but that's a classic exercise, right? Set this up in the best coordinate system. Okay, so any questions about this one before I move on to the next example? Because we're going to do more of these. Yep.
You could switch. I don't know if the theorem applies for this one, but if it's convenient to do d0 d theta first, can you switch around?
Yeah. So by convention, the way that I write this is dr d theta dz. There will be cases in which the dz has to be done first, right? The only reason we did dz out here this time, in fact, generally. If the z turns out to be a function of x and y, it will have to be integrated first. The next example I'm going to write down, it works exactly it will answer your question. So sometimes you can use Fubini's theorem and sometimes you can't.
Okay, it just depends on the conditions?
Yeah. Yeah, in this case you can because it's rectangular, right? Since these are all constants, you can do it in any order you feel like. Right? There's no composition of functions down here. You can just do whatever you want.
Yeah, but whatever is composed, you do that interval first.
Yeah, so if these have functions inside of them, you have to integrate the variables away before you put the constants in, because there will be variables left in the question when you're finished otherwise, right? Okay, so let's look at a question that I asked, or a version of a question that I asked, kind of a difficult question, I think, that I asked on the last worksheet day. So I want to know the volume contained between y is equal to x squared plus z squared and y is equal to 8 minus y squared minus z squared, or x in there, 8 minus x squared minus z squared. So these are two paraboloids. They're oriented along the y-axis this time and not the z-axis. So if I was going to draw this, I have one paraboloid that opens this way. That's the paraboloid. It's along the y-axis here. So this is the paraboloid y is equal to x squared plus z squared. And then in the other direction, starting at the point y is equal to 8, I have a paraboloid that opens to the left. And they intersect each other. Right? So if I have two paraboloids facing each other, they intersect each other in a circle. And I'm looking for the region that's contained inside those things. It's sort of like an egg. But there's actually a sharp corner right here. It's not a smooth corner, it's a sharp corner. And what I want to do is I want to figure out what the volume of this thing is. Now, you could reasonably set this thing up in standard coordinates, just like the last exercise. But if you do, the region that you're going to be integrating over is going to be a circle. And you're going to have to use square roots again. Right? The natural way of thinking about what's happening here is, well, I guess the first thing you should decide is, what are you going to pick as the base of this region, right? The sort of bottom of it that you're going to figure out a top and bottom of the region for. You got three choices: xy plane, yz plane, or xz plane.
XZ.
I'd probably choose xz in this case because the circle of intersection here in the middle, if you translate it back to the xz plane, would look like this. And every point here in the xz plane, if I was trying to figure out, can I describe the entire region by moving around inside the xz plane inside that circle? And the answer is going to be yes. If you go up, you start when you get to the first paraboloid, and then you're inside the first paraboloid until you leave it at the second one, right? So every point xz goes in the region from the bottom paraboloid to the top one. Bottom and top here being right and left. But so the axis this time, our height axis is the y-axis, not the z-axis. If I wanted to do this in Cartesian coordinates, I would be faced with this situation again. Oh man, I've got this circle right here. I don't even know the equation of the circle yet. But I have to somehow describe that region in x and y coordinates. And already, as soon as you see that the base is circular, you should be thinking that cylindrical coordinates are going to be the way to go. There's a circle down there. You should be thinking polar. Okay, what is the equation of intersection? How do I find it? I need to know this. I need to know the radius of this circle. How am I going to do it?
Set those two places.
Set them equal to each other. All right, so x squared plus z squared is equal to 8 minus x squared minus z squared. And if I've done this correctly, by the logic of textbooks, this should, of course, turn out to have integer values, right? So x squared plus y squared is equal to 4.
Plus z squared.
Z squared. And so the bounding circle is a circle of radius 2. So let's write a system of inequalities now that describes that region sitting over this circular base. It should be the case that our radius values go between 0 and 2 because that was inside of a circle of radius 4. We're integrating over the entire base, so our theta values are going to go from 2 pi, or be between 0 and 2 pi. Now the next choice we need to make is, notice that when I did this, when I took r and theta, it was the x and z variables that I'm translating into. X and z have been translated into the polar coordinates, not x and y. Our height variable this time is the y variable. So we're not going to use the standard cylindrical coordinate transformation with respect to the z-axis. We're going to do it with respect to the y-axis instead. So what I mean is, I want to use the coordinate system x is equal to r cosine theta, y is equal to y, and z is equal to r sine theta. These are the coordinates that I'm thinking of as the polar coordinates, and this is our axis, or our height variable this time. I can reorient cylindrical coordinates to be in line with the axis of the cylinder. Because this is arranged symmetrically around the y-axis, I'm going to let that be the variable that is the axis variable. Yep.
Does it matter what we choose to be r sine theta?
It does not actually. Yeah, the answer will be the same. Yeah. So that all you're doing is just introducing an orientation when you do that, and it will not change the answer. Okay. So with that change, that means that we know that we're looking at our y values, and our y values travel from the paraboloid on the left up to the paraboloid on the right. I guess I should have written the equation out here. 8 minus x squared minus z squared, which gives us the inequalities 8 minus x squared minus z squared and x squared plus z squared. Well, that's kind of dissatisfying because then we're supposed to have r's and thetas, and I still have x's and z's. Well, let's just write down the inequality, or the integral, and see if we can fix it. So if I'm trying to calculate a volume, I'm going to write v is equal to the triple integral over r dv, which according to what I've written right here, should be the integral from 0 to 2 pi of the integral from 0 to 2 of the integral of, okay, so x squared plus z squared, because that was this paraboloid, up to 8 minus x squared minus z squared, and then r dr d theta. Oh, I need a y in there. So r dy dr d theta. That was the y variable, that was the r variable, that was the theta variable, right? The y variable, the r variable, and the theta variable. Y, r, theta. I'm not quite done though, because I got those damn x's and z's running around in there still, so it's not polar yet, right? Or not cylindrical yet. How do I get rid of those? Yep.
Change them to r cosine theta.
Yeah, but I could do even better than that. What is the relation between x and z that's imposed by this change of coordinates here? X squared plus z squared is equal to r squared. When you choose this axis, you're choosing what the polar variables are, but you get all of the polar relations when you do that. So that means to finish this problem, to get all the x's and z's out, you could have written this as the integral from 0 to 2 pi of the integral from 0 to 2 of the integral from r squared to 8 minus r squared r dy dr d theta. So the natural way to do this question is in these coordinates, because you get this really nice limits of integration when you do it this way. All right, I have one more example to work through here, and it's going to be a motivation for introducing yet another coordinate system. All right, questions about this example before I go on? Yep.
Wait, so for the y-values, why is it defined as the two functions instead of just from 0 to 8?
Because when you pick a different value of x and z, like if I picked this one, I would go from this point to this one instead. And if I picked the one in the middle, I would go from the bottom all the way to the top. The x, y, z, the x, z value that I choose, I change, the surface changes, right? As I'm in the middle, I'm like this, and as I go out to the side, it comes down to nothing, right? So y is a function of where I'm sitting over the top of the base. Does that make sense? If it was planes, it would just be constantly equal to 1 and 8. Yep.
So if your like cylindrical axis is a function of the other two variables, you have to integrate that one first.
Yes.
What if r is a function of theta?
Then that has to go second. In fact, this is why generally I always write dr d theta. Because theta, in the conventional way of doing this, theta will never be a function of r, but r is frequently a function of theta. So like if I had done this over some region that had some horrendous edge, but it was still on an like angular chunk, and I had some function describing the outside, I would need dr first and then d theta. So in cylindrical coordinates, it's actually pretty typical to go height axis or height variable, radius variable, theta variable. Always just that's the sort of conventional order. Okay, last question. Good questions. Okay, so I'm going to build some motivation for 15.8. So one of the examples I had on the board last time when I said, hey, if these problems are too easy for you guys, you need something harder to work on, was I said, find the volume between the cone z is equal to the square root of x squared plus y squared, and the sphere x squared plus y squared plus z squared is equal to 1. So if I was going to draw a picture of that, this kind of looks like an ice cream cone. You've got this sphere of radius 1, and then you draw a cone that starts here, and the cone goes out until it hits the circle, and then you cut through. It's like you're cutting the rest of the sphere away. The shape that you get out of this, that's contained between them, is the interior of the cone and this cap of a sphere that has sort of been glued together. So it's like an ice cream cone. A cone with kind of like it's not a hemisphere up here, right? It's a cap of a sphere instead. It's not definitely not half of the, you can see it's not half of the sphere. Okay, so I want to know how to calculate the volume of that thing. And from what we know right now, you should think, okay, it's clearly another cylindrical coordinate problem, because there's going to be a circle that dictates where they intersect each other. That circle back here in the xy plane will look something like this. Every point that I choose in here with coordinates x, y, I will go up until I hit the cone, I'll be in the surface until I hit the sphere, and then I'll leave. So my setup this time looks pretty natural for cylindrical coordinates. I'm probably going to choose z. I can use the classic XYZ here because my radial axis this time is the z-axis. My height axis is the z-axis. And so if you do this problem in cylindrical coordinates, you have to set these things equal to each other. So the bounding circle is going to be where the square root of x squared plus y squared is equal to the square root of 1 minus x squared minus y squared, which is equal to, okay, so if you square both sides, you get x squared plus y squared is 1 minus x squared minus y squared, and so x squared plus y squared is equal to 1 over the square root of 2 squared. Circle of radius 1 over root 2. So my domain looks like this. This circle is x squared plus y squared is equal to 1/2. And I think my z values are stuck between the cone on bottom, which is the square root of x squared plus y squared, and the sphere on top, which is the square root of 1 minus x squared minus y squared. And if I want to do this in cylindrical coordinates, I'd say, okay, well, that's my height variable taken care of. Now I'm going to put x and y in terms of r and theta. That's pretty easy. R goes from 1 over root 2 to 0. And theta from 2 pi to 0. And if you want to continue this, you could say, all right, well, x squared plus y squared is equal to r squared. So what I should have done is I should have written z is less than or equal to the square root of 1 minus r squared. And down here, there would be an r. The square root of r squared is just r. So in cylindrical coordinates, the volume of that region looks like the integral from 0 to 2 pi of the integral from 0 to 1 over root 2 of the integral from r to the square root of 1 minus r squared r dz dr d theta. But it's like, there's something about this that kind of makes my brain itch a little bit, which is, one, I already know where this is going, so this is like typical math professor crap, where I know what the answer is, so I'm pretending like I don't. But if we imagine for a second, we could be irritated at the fact that spheres are just as natural as cylinders are. This is a pretty natural thing to want to be able to study, right? If I'm working in like a radar system, that sort of cone is like the sort of cone of emanation of the signal from the radar dish. If I'm studying astronomy, this is an arc of the sky that I'm studying, right? Like, this is a natural thing to want to look at, that kind of figure. Maybe we should choose a coordinate system where instead of having to have this mess over here where I've got r's and square root of 1 minus r squareds, maybe these should be the figures that are our basic shapes. Instead of cubes or cylinders, maybe these chunks of spheres should be our natural figure. Like, I'm going to break the entire world up into ice cream cones. What could be wrong with that? And so the motivation for 15.8, which I'm not going to do all of, but at least I'm going to introduce today, is I want to have a different coordinate system where this kind of region becomes very easy to integrate. Okay, so that is a justification for the next thing. We can do this in cylindrical coordinates. Now, before I talk about this, I will say there are a lot of different majors in here. Every single discipline has a different standard for what dictates spherical coordinates. So you may already be in engineering classes or physics classes where you've done things in spherical coordinates, and the way that you set them up is different than the way I'm going to do it here. I'm giving you the one that's in the math book and the one mathematicians use as the standard. So here's how we set it up. We have an x-axis, a y-axis, and a z-axis. And the idea of spherical coordinates is I could tell you where something is sitting in space by telling you how far to go in the x direction, how far to go in the y direction, and how far to go in the z direction. That's one set of coordinates. Or I could tell you rotate by this angle, go out this far, and then lift vertically up. Or I could say rotate this much, then rotate vertically, and then extend along that ray by some radius. So 2 angles of rotation instead of 1. 2 angles and a radius is what spherical coordinates are built out of. So we have this privileged, let's see. So I'm going to give you a point x, y, z, just like before. This point up here in regular Cartesian coordinates is x, y, and z. This is how the spherical coordinate system is set up for mathematicians. The z-axis is sort of like our pole axis. It's important. And we have these measurements to make with respect to it. So I'm going to draw the vector that connects the origin to the point. So that's the line from the origin up to the point x, y, z. The length of that line segment is rho. That's like the radius of the sphere that that point sits on. So the length of this is the letter rho, if you've never seen that before. spelled RHO. It's like a curly P. So the distance of that arc. The angle between the purple line and the green line, so this angle right here, that angle is called phi. Probably you guys have all seen this before, I'm going to say it anyway. So that angle is the angle phi, and I still need a theta, and so the way that I get that is I connect in the xy plane, I connect the pole to the shadow of the xyz point, and then this angle right here with the positive x-axis is theta. I'll write this out just because if I'm teaching you the Greek alphabet in miniature, it's not. Okay, so the natural ranges of these things, right, where these things can vary, is we let theta go between 0 and 2 pi. Rho can go anywhere from 0 up to infinity. So a positive radius extending forever, basically. And then phi, well, if I'm measuring from this axis down, I don't need from 0 to 2 pi because that would be like wrapping back up around again and getting back to where I started. I can uniquely determine every point by just letting phi run between 0 and pi. So, again, if you want to think about how the polar coordinate or the spherical coordinate system works, oh yeah, I guess a yardstick. All right, so if I want to dictate where a point is at, it doesn't really matter what order I do it in. I have my positive x-axis that I'm pointing in. Theta rotates me in the xy plane. Phi is, okay, so yeah, so theta is a rotation this way. Phi is on this plane right here. Phi says start there and then rotate down by an angle of phi. And then the rho just tells you how long to travel along the stick. So the theta sets up a plane that you're going to rotate in. Phi tells you how far to go this direction in that plane. And rho just says go that radius. 2 angles and a spherical radius. And if you do that, I've debated about whether or not I'm actually going to derive this or not. If you trace through what the trig says about all this, the relationship between x, y, and z and rho, theta, and phi is x is equal to r times the sine of phi times the sine of theta. Y is equal to r times the sine of phi times the cosine of theta. And z, it's not r, it's rho, sorry. Rho, and rho cosine phi. Yep.
Do you always do it like that with phi coming from the top, or can you do it from the x?
You can do so you can set up spherical coordinates with respect to any of the axes. And so, for example, if you were working in aeronautics or control theory of some kind, a lot of times the axis that you set up as the main axis is actually the axis of motion. So if you're in an airplane traveling, you want your spherical coordinate system to be relative to the direction that you're moving. And then instead of going from 0 to pi, you go from minus pi over 2 to pi over 2 instead. So there's a lot of different ways to set this up. So this is just an arbitrary setup because it's the way mathematicians do it,
Okay.
right? So yeah, even with this setup, if your problem is set up where there's a natural sort of axis, like a main axis like this, you can rotate the whole system so it looks like that. Yep.
What's going on with the row on like the left, like the zeros between row?
Oh, it's supposed to be infinity.
Oh.
Rho can take on any value. It's allowed to take on the value 0, and it can take on any. I mean, it's like x and y and z can go from minus infinity to infinity. Rho is allowed to start at 0 and then go to any value you want, right?
Yeah, I thought it was theta at first, and I was really confused.
No. Theta just like whipping around. A highly non-unique coordinate system. Okay, so as an exercise, now there are formulas for calculating rho and phi and theta from x, y, and z, but because this way of thinking about things is really unfamiliar to most people, and I've had a lot of trouble with this in the past with students, let's just find some polar coordinates geometrically. Because the geometric approach to finding the polar or the spherical coordinates actually will show you what some of the difficulty in thinking in spherical coordinates is. Let's just figure out what the spherical coordinates of x, y, z is equal to 1, 1, 1 are. So if I have the point 1, 1, 1, that's about as easy as a point gets, right? So I go 1 unit in this direction, x, and 1 unit in this direction, y, and 1 unit in this direction, and there's 0.111. How should I start? Here's a good place. How about we connect up the pole, or the origin, up to the point, and then rho is the length of that vector. So what's rho equal to? Rho is the square root of 1 squared plus 1 squared plus 1 squared, which is root 3. Theta is actually not too bad either, because if I drew this line segment right here, and then I just restricted myself to the xy plane, that red line would be right here. This would be 1 unit in this direction and 1 unit in this direction. And theta in that picture is the angle from the positive x-axis. Aren't the coordinates of this point in the xy plane just 1, 1? If I just look at the xy plane, it's just 1, 1, right? So what's theta?
45.
Probably we want to work at radians and not degrees, right? Like, it's not terrible to work in degrees, but like, because this stuff is all set up, so the formulas are, we should probably just think these are naturally in radians. Now, if we wanted to, we could solve for phi by using trig, because I already know z is equal to rho cosine phi, but I don't want to do that. I actually want to extract this information from a triangle, which is to say, now, maybe I'll put the green side down here. So the triangle that I drew right now, this green triangle, should be careful, is this green, oh damn, I ran out of time. Okay, so the green triangle I drew here is the green triangle at the base. What we'll do next time is I'll show you how to take the vertical triangle here, and if I drew its picture, so this triangle does not sit neatly in one of the planes. If I drew it, it would look like this. This side would be length root 2, this side would be length 1, this side would be root 3. The 1 comes from the height. The root 2 is the length of that side right there. And the angle that we're trying to find is this angle. As was pointed out by somebody in the last class, that's actually the same as this angle right here, because you have a transverse cutting of parallel lines. So what should phi be? You can use trig. Tan phi is equal to root 2 over 1. And that's the best you can do. Phi is equal to the arctangent of the square root of 2. That would come straight out of this relation too, if you like. It looks like a cosine instead of a sine. All right. Spherical coordinates. Take some practice getting used to. So next time we'll talk about how we integrate in this setting.
Thank you.
Yep. See you guys.